Okay, good afternoon, everybody. Happy Monday. So quick announcements. You guys should have quiz 1 up. You guys should be accessible to it. You should have tried it at least by now, at least once. Remember, it is due on Friday at 5 p.m. We'll close. Again, it will auto-close at that time. Please make sure you've done and submitted it with plenty of time to go. Today also office hours, so I will be over in Chem 215 if you need any help. Last class, we introduced the olefination reactions. This is the Wittig reaction and the HWE Horner-Wadsworth-Emmons reaction. The difference between these two, the approach is very similar, the mechanism is very similar. This is about the geometry of that first intermediate. This is the molecular patty cake example that we went through, right? The general approach, and we'll go through this one more time, very similar. It's just about the relative stability of that first intermediate, whether or not it's rate limiting. So based on those, how would you prepare this molecule via a Wittig reaction? What's the reagents you'd need or the disconnection you could do? Okay, turn to the person next to you. Talk it out. What are the answers? Are you right? Are they right? Are there more than one correct answer? Okay, time. So if you're taking this apart, you're trying to look at this from a retrosynthesis. First feature that we've given you, it's a Wittig reaction, which means players we're going to use. We're going to be using some kind of carbon minus with a pH3. That's our phosphonium ylide, or the ylide part of it. That's one of the two key pieces of our Wittig reagent. The other one, the other player, that's our nucleophile. The electrophile is going to be some kind of carbon compound, right? It's a carbonyl, aldehyde or a ketone. That's the two parts we're coming through. The rest of the reaction, when we make this new carbon double-bonded carbon, we're going to be making a phosphorus double-bonded oxygen at the same time. So if you're actually sort of following through where all the pieces go, that's the sort of the overall disposition through this. Now, there's two different polarities. You can call one of them nucleophile, one of electrophile. If I was going to say the nucleophilic carbon here corresponding to the Wittig reagent, the electrophilic carbon is there. Now, this is a decision you can make. Either polarity is possible in most cases. So if I did this, I'm saying the nucleophilic carbon is from this one. I'm saying this half of the molecule actually comes from where that carbon center is attached to P phenyl, positive, negative, or you can draw it as the carbon-carbon resonance isomer, right? That's my nucleophilic fragment. As soon as I've defined that, the electrophilic fragment becomes that carbonyl, that's acetone. So it's a nucleophilic primary carbanion adding to acetone to my ketone in this case. One step back. So I'm done here. I don't know to go back any further. Where does this come from? Where do I get this molecule? You have to generate this. How do I make it? Yep. Yeah, that's right. This part here needs to be installed. You need your negative charge, you need your triphenylphosphine. This comes from an SN2 reaction typically. So it comes from one more step back. It would start from same molecule, that carbon here tracking all the way through. That one is that one. This would be a leaving group, good leaving group like an iodine. And I would form it in 2 steps. Usually I add my phosphorus bit, so triphenylphosphine. And step 2, I'm going to add this with a base, usually butyllithium, right? And butyllithium or LDA, strong base. So it's that double sequence to generate your ylide, and then you bring in your carbonyl. So it's a total of 3 steps altogether to get to your final product. The other polarization also potentially works, right? You could have the red part being your carbonyl, in that case it would be your aldehyde, and then the blue part would be my ylide. There's some discussion, like I said at the end of last class, sometimes for certain molecules, there's what you call preference. Why do I like putting the iodine, primary iodine, as my preference for my ylide formation? What's an advantage of putting the iodine on my primary center compared to maybe the iodine on the secondary center? Yeah, like since I have, if you think about it, I need to do this reaction. This reaction is the real fun, that's the centerpiece, that's what I care about. To get to this molecule, I need my nucleophile. My nucleophile is hidden between 2 other steps back to my starting material. If the very first step is an SN2 reaction, and I've got a bunch of more steps to do, start on a really good foot, use a really good SN2 reaction at a primary center. Again, this is not the only way to do it. I'm just mentioning this from a synthetic or lab point of view. That's why we often see it in this sort of polarization. But both of those two are possible. Okay, so today we're going to finish up on the HWE mechanism. We're going to finish off that part, and we're going to introduce enols, enolates, and keto-enol tautomerism. Some of this is review from your second-year classes. So we mentioned last time, unlike the Wittig reagents, HWE, what makes them unique is the nucleophilic carbon is still attached to a phosphorus. Instead of being a trivalent triphenylphosphine, now you've got these carbonyl-containing phosphorus, these phosphonates, right? Those phosphonates are always flanked by an electron a resonance stabilizing group. On the other side of that carbon minus, not only do I have this phosphonate, this phosphorus double bonded oxygen already baked in, so I already have some amount of resonance stabilization helping me here. I also have resonance stabilization on that side. What this generally does is it takes that carbon minus and it makes it way more stable than the classical ylide that we're dealing with, the triphenylphosphine. This stability matters for 2 reasons. I can now use much gentler bases. So sodium hydride or t-butoxide, these are much more kind of typical run-of-the-mill bases, not the stuff that's going to melt your face, like t-butyllithium or something like that. So that's very useful from just a structure perspective. We've got a more acidic hydrogen. These guys now drop in the sort of the range of things like alcohols now. Having those 2 stabilizing carbonyls means that the protons in between are much easier to deprotonate because the product, the anion that we're forming, is much more stable. That equilibrium now lays a little bit more in favor of that product, which makes the protons easier to deprotonate. So that's just a practical point of view. The other big one, though, is it allows us to switch the geometry of my olefination. Now when this reaction is done, my bulky R group and the other payload are now trans to each other. They're on opposite sides. This is the opposite kind of general sort of disposition we saw with the Wittig reaction. Wittig reaction put the 2 bulky groups on the same side. This one will put the sterically bulky groups on opposite sides, generally forming the E-alkene. Now, one thing to focus on, though, it's not exactly apples and oranges because remember, yes, this could be any aldehyde. I could use the same aldehyde both with the HWE reagent and with the Wittig reagent, right? But let me quickly draw that out. The Wittig reagent I would be aiming for here would be, let's say, pH3, right? Negative, positive. If I wanted to go 1 for 1, so I want the same payload as I have here, like this, right? So what I'm trying to do here is only change this portion of the group. I've switched it over to my normal one for I have triphenylphosphine. What do you think happens here, though? Is this a stabilized or unstabilized ylide in this case? The one I just drew on the bottom. So who's in camp has resonance? Does this have resonance stabilization? Yeah. This kind of falls in that camp of this is a stabilized ylide. So this is not a one-to-one comparison. It's not like I can take this reagent and go, oh, look, I've got E. I'm going to switch it to triphenylphosphine, and I'm going to perfectly switch to this side. No, this is still kind of in that same camp. This is still resonance stabilized. It's going to be some weird hybrid. If anything, it's going to act a little bit more like HWE. If your ylide has resonance stabilization, like you see here, you'll still see this general geometry win. It may not be quite as high. Going to this guy, you're going to see like a 90% of this. This one will still see 60, 70%. It's still a stabilized compound. What I'm saying is that from a perspective of, like, say, Wittig, classic Wittig would look like R group. No stabilization at all, like a, let's say, just butyl chain or something like this. Simple carbons. That is way clearer because in a case like this where you have only triphenylphosphine and just simple carbon, there's no stabilization present and bulk wins. Yes?
Stabilization on both sides, how do you know which side?
Say that again?
You have stabilization on both sides, how do you know which side?
You have stabilization on both sides of what, sorry? Oh, like, but in order to do that, that's mean I would need this, right?
You know, like, if it's not a phosphorus on the left side, it's another stabilization, how would you know?
Oh, if you don't have a phosphorus, ain't no Wittig, doesn't exist. Remember, the phosphorus is there to act as, it is there to disappear with the oxygen when the reaction is over. It's a critical part of the mechanism to make it work, because its job is, yeah, it's stabilizing the negative charge, but the second part of its job is right here. It's the guy grabbing that oxygen and bugging out. So you need it as part of that system. Yeah. Make sense?
Can it only work with aldehydes or can it work with
Aldehydes and ketones, better with aldehydes just in general. In general, you'll see it with the aldehydes component. Okay? Any other questions? Yeah. So, sorry, back here, can the sulfur act the same way the phosphorus does? No, in fact, right here, nice thing about that, sulfur here is at the highest oxidation state. It's not picking up any more oxygens. So in these examples, think of this part right here, as just the payload. All of these are transferred in where they would take the place of this group in that position. They're not acting as an elimination catalyst in those points. No, sulfur is not going to act in the same way as phosphorus. No, not at all. Yep. No, good questions, guys. Any other questions? Okay. So the mechanism of this follows similar through we've done. I make my negative charge. That negative charge is going to undergo a nucleophilic attack. Now the key, why this works out, just like before, we're making this, charge stabilized intermediate. It's like the betaine that we formed before. Actually, let's switch colors. So this is my nucleophilic fragment at that center. O ethyl. And then over here, we've got our PO. So in this first intermediate, we're doing the same kind of an addition to form our phosphonate. Now notice here, we're starting off not with an ylide, we're starting with an authentic anion, which means there'll be some balancing carbocation, X+, that would balance against this. This would be formed by something like sodium hydride, so this would be probably your sodium metal as your ionic equivalent, which means this is still stabilized by that cationic surrogate, whatever came in with your nucleophilic part. So it's no longer a zwitterion, we have this sort of captured oxyanion. From there, it's still going to form a similar compound. Remember, this is going to be a rotation about this center. The oxygen is going to attack into the phosphorus. Because this is a carbonyl, you can think of it kind of like the aldehyde again, too. So that addition, you can draw it as 2 electrons into the phosphorus center, and then you're promoting that phosphorus-oxygen pi bond up onto the oxygen center. So after that rotation, and we have a new bond between those two centers. So this is the equivalent of our oxyphosphatane. It's a 4-membered ring just prior to our elimination. Last step is to fragment this bond. And again, what we're doing here is we're going to be forming an oxygen-phosphorus double bond and forming a carbon-carbon double bond. So when we're finished, we have our new carbon-carbon double bond, and that fragment. And we've eliminated this species. This now will be our phosphorus double oxygen, O minus, O ethyl, O ethyl. So similar mechanism we've worked before. The big difference here is in that very first step. Remember when we had, for the Wittig, this nucleophile we say is very unstable. And again, unstable relative especially to this guy. This guy has resonance stabilization. Which means if I have a really unstable nucleophile, I find an electrophile, that reaction is going to happen and it is irreversible. It's very product favored. Think of it as one way only. In this case, since I have a stabilized nucleophile here, this first addition is reversible. That's the big difference between the two. Basically, I can add, and yes, this oxygen is going to through that bond rotation, has to attack the phosphorus. We got to get to this 4-membered ring just like we did before. The difference now, though, is the geometry of where these bulky groups are, this R group and this, it can still play a part. So back to molecular patty cake. If I take my carbonyl and my carbon phosphorus, you're always going to go in still anti to each other. That addition is still the same. Heel to heel is your carbons to each other. For the Wittig reaction, that addition, carbonyl one way, carbon phosphorus the other way, 180 degrees, that's enforced. My two thumbs opposite each other. This is the stable first intermediate, and it's irreversible. It forms, I'm done. Then the rotation puts them on the same side. My elimination happens. I'm stuck with syn. That's the consequence of that first addition. But I don't have a choice. That first addition wins. Putting them on this way, two thumbs on the same side, does not happen. Too high energy. In this case, I can do that first addition. It goes to rotate and goes, ooh, this is not cool. I don't like this. So in fact, you know what? If I go back and I reverse and try the other side, yeah, this is kind of painful. It's not the best first intermediate, but it gets me to the most stable 4-membered ring. Because that first addition, this is the fast and easy, it does not lead to the intermediate you need. What you get is an equilibration where it's actually easier to break up, try again, rather than force your way through to an elimination. Since that first addition, you have both sides that are possible. Eventually, the higher energy first intermediate wins to get you to the more stable final product. That's what's generally going on here, and it all comes down to the relative stability of this and that first intermediate. So this is what we're just dictating out in this part. You can think of that first addition under equilibration to, yeah, I generate a higher energy intermediate, but it gets through to a more stable product. This is what we would generally call the difference between a kinetically controlled process, that's the Wittig, the fastest product, the easiest one to get initially is what I make, an irreversible reaction, versus a thermodynamically controlled process. Yeah, I might make a high energy intermediate, but overall, over the long run, I make the thermodynamically more stable product, generally. Make sense? So, we've got a couple examples for you guys to work through. Again, I will do these longhand as our practice try it later problems. Each of these is meant to walk you through ways of going through these different syntheses, and I want you guys to take a look at them after they're posted up, give them a try, and I'll do them as a pencast after. So now we're going to start walking into these new compounds. And first, when we're talking about compounds like this, we use a Greek letter nomenclature to talk about how far away from the carbonyl we're dealing with. You may have heard this before, where if we're talking about reactions at this carbonyl, the alpha carbon is referring to the first carbon 1 sigma bond away from that carbon center. And we're talking about walking along the carbon skeleton. Beta is 2 out, gamma, and delta, right? So we're walking out, and this is basically the designation is how far away from that center carbon we have. Why this matters is, for things like ketones, I have 2 alpha carbons because it's both sides are flanking this one. If this is an aldehyde, I only have a single alpha carbon. Why this matters is we're talking about different reactions which will affect the alpha carbon, the nature of what's substitution there, what other groups we have there, if they're electron donating, withdrawing. Those will actually have differences in the pKa and the relative stability of things like double bonds or other components. So when I refer to things as far as positioning, this Greek letter designation is how far away from that carbonyl we're dealing with. So for a molecule like this, these protons matter because now what we're doing, if you imagine doing elimination reactions or general acidity, things like enolates are going to impact these alpha protons over here. These are what we call also exchangeable protons. The relative acidity of these changes because the further away you get from that carbonyl center, everything that stabilizes deprotonation or reaction to them changes. Think back to this. If I was going to deprotonate this, let's say I go in with a strong enough base, that center, that deprotonation is not too bad. Why? What's missing? What else? How do you rationalize that those alpha protons actually are not that bad in terms of relative acids, especially if I use something like t-butoxide, if I use sodium hydride. These guys are fully in scope to be deprotonated. Why? Exactly. If I was to blow away this center, let's say a base has deprotonated it, I make a negative charge here. Yes, it's a negative charge, carbanions are bad, but just like we talked about with Horner-Wadsworth-Emmons, a negative charge where right next to it I have a carbonyl. Yes, I've got inductive help, right? This center here is delta plus, but bigger is I've got resonance help. The negative charge that you would basically put on that center actually draws out that charge and spreads it over 3 centers. It's the same reason, you guys go back to this, what's this functional group called? And this is what's the pKa of that proton? 5. What's the pKa of this proton? And that's because, same thing. We're saying alpha to this carbon, I make a negative charge, I can be acidic because resonance. This is just the carbon equivalent of a carboxylic acid, right? Sorry, I saw a question over here. Cool. So yeah, that pKa drop, that acidification is exactly the same thing you're seeing in this part here too. Now, what that means is I'm going to form and start working through these different tautomers. These are different structures where they're, again, on the same oxidative energy surface. The difference between them is where we have our protons. The keto-enol are what we call tautomers to each other. They're the same molecular formula. They are isomers. The only thing that makes them different is here I've got 2 protons and no protons. Here I've got 1 proton, 1 proton. Somehow that proton has ended up on that oxygen center. The keto-enol molecules are, quote unquote, the same, but they're isomers of each other. They are not resonance structures. They are keto-enol isomers or keto-enol tautomers. Quick guess, which is more stable, keto or enol? Keto, right? Why? Oh, CO pi bond, not just pi bond. You got a pi bond here too, right? You got a CO pi bond in that sort of case. Yeah, exactly. The carbon-oxygen pi bond will win over the carbon-carbon pi bond. It's also because there's a diet named after it. But there's no enol diet. There's the keto diet. That's all. And also, too, up until now, you probably haven't seen enol structures. Enol structures, we don't draw them because that's not how you find these guys out in nature. They are the minor isomer of this particular equilibrium. How we form them and the reaction we're going to use is also using this thing called an enolate. Now, this ending here, remember the iminium, IUM, that was the positively charged species. These are anionic structures. They're generally thinking them as Nucleophiles. They are carbon nucleophiles as well too. We'll be using these to do carbon-carbon bond formation. So the enolate is a partner or comes from things like the enol, where we're deprotonating at the oxygen center. So enol versus enolate, what we're doing here is we're deprotonating that center, and just like the normal alcohol, that's a pretty acidic proton because it's not just like a normal alcohol. If I were to deprotonate this, I have resonance stabilization. It's not the greatest resonance stabilization because we're putting a negative charge down into that carbon center, right? But as I do this, right, if I do this deprotonation, they are in conjugation. They're better than just sort of a normal alcohol, and they can be formed by treating it with a base. It just means that on this energetic surface, we've got these compounds now, these enolate type structures, where the alpha center, if we deprotonate them, will exist as these two resonance isomers. So if I were to take this structure, move them that way, I make my enolate form versus the carbanion form. Going back way this way is how I get back and forth between the two. Now remember, these two, now that I've deprotonated, these are resonance isomers of each other. I'm just moving around pi bonds. Keto, enol, not resonance structures. You got to move around sigma bonds to go between the keto, enol two structures. Of these two, left or right, what do you guys think? Which do you think is more stable? The carbanion kind of structure or the oxyanion kind of structure? If you had to give them a ranking, carbon or oxygen, which one wins? Why? What's your rationalization? Yeah, oxygen's more electronegative. It's better able to hold on to a negative charge. So if you imagine, if you could separate these two, this is probably the center way we would draw in a Lewis structure the personality of the molecule. It's going to have pretty high carbon-carbon bonding, double bonding. It's going to have mostly an oxygen minus kind of center. That's how it's going to exist sort of like most of the time. But remember, these are resonance structures. We're not talking about freezing these two out. You cannot isolate the two. You have to keep in your head that both structures are accessible. You can do reactions from either of these two personalities. Now, because of that, if I'm going to use this like a nucleophile, it means I'm nucleophilic at both. It's nucleophilic at both. Oh, you stupid pencil. Yeah. It's nucleophilic at the oxygen, delta minus. It's nucleophilic at the carbon, delta minus. The real molecule, if I was going to draw this out as like the resonance hybrid, I could draw it as a dotted bond across here, my R group over here. This is my hydrogen R prime, and a delta minus at those two centers. It has this duality at both centers. Now, if the carbon minus, we said before, carbon minus is more reactive, how do you think this is going to react most of the time? As a carbon nucleophile or as an oxygen nucleophile? It actually will play with the carbon. Even though the stability, think of it this way, if the O minus is more stable, if you had to think of those two, holding the negative charge in the oxygen, that is happy. If something's happy, it is not reactive. The carbon minus form of it, because it's this higher energy sort of disposition of that negative charge, is where you're going to get your nucleophilic attack from. It means it's going to store the negative charge on oxygen, but use it on the carbon between those two. Sorry, yeah?
Yeah, quick question. Do we specify if the enolate has like a different name if it's a aldehyde or a ketone?
No, an enolate is just, enolate is this. Enolate is just this negatively charged, resonance stabilized, negative at carbon and oxygen. Aldehyde or ketone, you could, I don't think there's a difference between a keto enolate or an enol enolate, just enolate. Sorry, yep.
Yeah. By an exam, would we ever be allowed to draw resonance in using the shaft line?
What do you mean?
I remember Professor Savage last time mentioned that no known to shaft line.
Wait, so let me repeat the question. On an exam, are you ever allowed to use a double bond to denote resonance? Like this, you mean? So again, let me paraphrase. This dashed line here refers to the, what do you call it? The, why am I blanking on the name? Resonance isomer. It's the general way to say that the average sum of all resonance structures, I'm trying to imply by saying dashed line or partial bond, right? If the question is asking you to show me where that full delocalization is, that's your best representation. If the question is asking you to say, show me all the resonance structures, then no, do not do this, right? This is trying to tell that you're trying to acknowledge with that sort of dash bond that there's an average or not a full bond because you were trying to say it's delocalized across the system. I think what he's probably saying for sure is this is absolutely freaking terrible. Do not draw the power donut and stuff like this, right? It'd be, if you're going to try to draw this in a specific way, generally, and this is just, again, think of it in terms of mechanistic practice. If you're talking about a mechanism where we're showing where bonds move, this notation is way more helpful to you because you're talking explicitly about where two electrons are, so you can draw where they're going next. If I were to draw this and then try to draw two electrons, it gets really weird, right? It's like bad penmanship or bad, that's, I guess, the way I'd sort of do. That's the best I can possibly sort of break out. I heard that laugh. It's okay. Okay. So, two sides. Enolates, negative charge, are resonance structures, carbon minus, oxygen minus, and they act like carbon anion structures. They're carbon nucleophiles. Keto-enol, they are tautomers. These are isomers. The reason why is that proton needs to break this bond, form this bond. There's physically a difference in what the sigma bonding skeleton is. These are not resonance structures. They are isomers. They're part of an equilibrium, right? Now, in general, yeah, the keto form is going to be a lot more stable. The carbon-oxygen bond is more stable than the carbon-carbon bond. It basically gives us the most electronegative center with that pi bond. That's how we generally would draw it. Now, again, there's certain systems where the keto form is going, or the enol form, excuse me, is going to win. Can anybody think of one just off the top of your head? You probably have run into it in different structures. If I drew carbonyl like this, that's definitely going to be more stable. The keto form here is more stable than the enol form, right? Everybody agrees with that? This guy wins. Choink, right? What happens if I do this? Left or right? Left or right now? Yeah, this is getting, why? So left starts kind of winning. Why? Yeah, your resonance in this form here, in this isomer, I have an uninterrupted resonance. Here I've got a skip, right? I got a CH2 in between there, no resonance between those two. What if I do this? Left or right? Everybody should say in one giant creepy voice, it is the why? Aromaticity, right? Now that I've made an aromatic molecule, that's going to win. Do you guys know what that guy is? Do you remember this name? This is something you guys may have run into. Benzene with an OH attached. We call this phenol. It's a horrible smelling antiseptic and stuff too. Yeah. So those are cases where, again, we can perturb this equilibrium. Point is, yes, these are not resonance forms. We're moving a proton, but it can actually move around where that stabilization goes depending on what else is on there. Now, the enol formation can take place under both acidic or basic conditions. You have two different mechanisms. So we have proton catalyzed and we have anion or base catalyzed. So we're going to start off with the acid catalyzed one first. Now, this should follow back with what we did with aldol, so the acetal and the ketal. Remember, under protic conditions, acid activator, what was the first move you guys did when you started off with a carbonyl and you're trying to make a hemiacetal or a hemiketal? What do? Protonate the carbonyl. When you're starting off with this, I have my electrophile. That means I'm going to start off where I have electrons. That's going to be my carbonyl center. That's going to be this where my kickoff. So under acidic conditions, you start by activating the system. Okay, and we're going to leave this. That's your water or your charge carrier for how the system goes. Again, generally, we'd say the equilibrium probably favors the starting material. You're starting with an oxy plus, like a H3O plus, and you're putting a proton onto an sp2 center. Equivalent probably still favors the sp3 oxygen plus. Okay, but once we've got this, what we just did, remember what we're trying to do or where we're trying to get to, if I draw our final product here, we're trying to get to O, where that hydrogen, you can think of it, it's up there now. We got to have a double bond between those two centers, and we've got our HR over here. We have only one hydrogen left here. So I'm losing a proton from here, gaining it up there. First step is good. We've just added the oxygen. It now has a hydrogen. We've got half of this stuff done. As we did that, we have now acidified. We made these protons even more acidic. Remember, they are acidic to begin with because deprotonating that center is stabilized by the carbonyl. Having an oxygen plus up there helps me even more, which means super simple bases. Just for equivalence, I'm going to use that to grab here, which does that, which does that. That's going to give me my final product. So I lead off by protonating the carbonyl. That makes the carbonyl more activated. It's drawing electron density towards it. That's going to acidify the alpha center even more. I have protons that could come off of the oxygen or the alpha center. By deprotonating the alpha center with a simple base, I set off a cascade where the double bond is going to migrate in to give you this product. So that's the good copy version of this. Now, I've drawn one geometry of my enol. Is this the E? If that's an R group, let's assume that this R group and this R group. Cis or trans? This is trans. Which do you think is favored? Both can form, right? But what do you think is lowest energy, if you had to guess? Why? Sterics. This is a key thing. This is an acid catalyzed process. Most of the reactions we're going to give you, you have control where you can equilibrate. The thermodynamic geometry is most of the time what you're going to follow, right? There may be cases where, because of a ring or something else where the rotation is not possible, you may be able to enforce a certain geometry. But by and large, this is under equilibrium, so you're generally going to make thermodynamically favored geometries. Okay, base. Just like, oh yeah, please.
Instead of R group is a hydrogen, which one would be favored?
What do you think?
The cis structure is the hydrogen group.
Yeah, maybe in terms of geometry, if this was a hydrogen, these are your two big groups across this, maybe. Again, under those cases, what you'll see is where we typically end up using these, the geometry you have here is transient. We form this because we're about to do something with it. So if you use the aldehydes, what you'll see as a consequence, it comes out in the wash, it won't matter, right? So the geometry here is a lot less important for what we choose to do with it next. The keto ones, you'll see some cases where that comes up. That's the one that's it's a lot easier to define. Base. This is the same thing we did with the acetal-ketal. Now you're starting with a negative charge. You cannot activate this carbonyl, so you're going to lead off with deprotonation. So what we're going to do here, and again, I'm drawing it right now as the sort of extended structure. You could, if you want, only draw the deprotonation like that. If I drew it in this way, I'm going to just explicitly stop there. Negative structure, hydrogen, HR, and water. So again, just for emphasis, I could just do this. That's my standard single bond deprotonation. Nothing wrong with this. Remember, that is part of a resonance system. So I could draw out the other half of this, the stabilization, get me up to O minus HR. Key thing is, under acidic conditions, you have cationic intermediates. Under basic conditions, anionic. Yes, please. Wouldn't the O minus just add into the carbonyl? Good question. So the other option would be, you know what, I'm just going to go do this. If you did that, O minus, OH, HR, right? Now what do you do? Protonate the O. So you mean, again, I'm totally going to follow this little rabbit hole. OH, OH, HR. What do we call this? We had a name for this specific structure, but again, let's say if this was alcohol, like water, we call this a hydrate, right? If this was an alcohol, this would be a hemiacetal or hemiketal, which is stable for isolation or unstable. This is a trap. Basically, some of your stuff could be stuck down this hole. You could form this, but if you wait on time, it will still reverse. With a strong enough base and a strong enough system, eventually all of this will drop over here, and you will still end up with protonation. Bloop, bloop. I'm going to grab that proton to make my enol geometry. So you're right. It's not that you can't do it. It's just that you can access the enol form from here. Now, how we make this reaction work, if we're going to do something with it, the enol form, you're absolutely right. Well, probably under most conditions, this is going to retro back to your ketone. If I make my hemiacetal or my hydrate, it's going to retro back to my ketone or aldehyde. Absolutely. The secret for making this do something for this is I need to form this species and then give it something else to trap it into another component. I need to use as a carbon minus species, or I've got to use as a carbanion, which is unique to this particular structure. You're not wrong. It's just that it's unproductive. Make sense? Yeah?
In the structure in the top right, is the oxygen with the negative charge taking the hydrogen off the water?
Oh, sorry. Let me, here. Bloop. You can draw it from the, yes, sorry. I was doing it the other way. Crap. I was using it as a carbanion. To get to the enol, I was too excited. I wanted to use it as a carbanion. Oxygen minus picks up that proton to here to form this new OH to make my enol. Yeah, thanks for that. I was trying to use it as a carbanion. So these are how, under the acidic or basic conditions, you can get to this kind of enol structure. This is how we move back and forth. Now, why this matters, or why we sort of focus on this, is we can use this as a tracer. We can look at centers within a molecule of where acidity or how acidic alpha centers may be. Exchangeable protons is usually what we describe them as. So if I took something where this was, let's say, instead of hydrogen, if I used a simple heavy version of hydrogen, what isotope do you guys know is a heavy version of hydrogen? It is deuterium. So what I can do is I can use examples of this to go back and forth. We can go through these different sort of examples. These structures, so the deuterium labeling is one way we can look at a molecule and probe where centers of acidity or reactivity may be. This is a common question we have you guys work through, is that given sort of structures like this, aldehydes and ketones, how many exchangeable protons may you run into? We'll go through that in just a second. But let's work through this. What are the enols that you could possibly form given this acid-activated carbonyl? The question behind the question, what we're trying to focus on here is, how many different enols could I make? 2? I see 2. Any more? Think of both isomerism and geometry. So let's look it out. We've got 2 protons here. How many alpha protons on the other side? Yeah, remember, stick into space is methyl. There are 3 protons. So I have left and right. One way to say this is here in this molecule, I have a total of 5 exchangeable protons. Overall, I could deprotonate to the red side or I could deprotonate to the green side. Okay, let's use the green. If I did that, the enol I could form over here would be OH, double bond, hydrogen, hydrogen. E or Z? Doesn't matter. Those 2 hydrogens are the same equivalency, only that, right? If we go to the other side, deprotonating at the red center, double bond, OH, CH3. E or Z? This is the most stable. Is there one more I could form? right? There are two possible enolates that I can, enols that I can form from that side. Yes, the most stable is the one on the left, the trans geometry. Cis is still possible. These are all three geometries that I could potentially form in this structure, right? And if you're counting it off, I have 2 exchangeable protons here. I have 3 exchangeable protons there. What I mean by that is if I ran this reaction long enough with deuterium, with plenty of deuterium, I would end up replacing all the exchangeable protons. Because what's happening is these are equilibria. By deprotonating at the alpha center, I create a center that is carbon negative, which means if it returns back to the keto form, it's going to pick a proton off from the solvent. If that solvent happens to have deuterium, it will be incorporated into it over time. We can add a label into this. This is a common thing that we use for all sorts of other tracers. In the end, though, looking at just these two, we end up with 2 different geometries to the higher substituted or the lower substituted. You guys know this from alkenes and elimination chemistry as well. The higher substitution, what we call the Zaitsev-like, this is thermodynamically stable. Now remember, go back, alkenes. Why did we say that is thermodynamically the most stable form, highest substitution? You guys remember what makes that more stable? Yeah. In the end, yeah, like what you have here is these are the same rules that you applied for your elimination. Higher substituted alkenes in general will be more stabilized because what we're not doing is we're not stretching out. Remember, these are going to act like kind of like carbocation type centers. In the end, the kinetic one is this one, the least stable. Now, kinetic, why does that seem to make sense? Why does this kind of, the one out to that methyl group, why would that be faster to form? What are 2 reasons why that might sort of win for you guys? More accessible, it's not baked into the ring. What else? How many protons on that center compared to the other one? 3 to 2, right? I've got 3 protons I could deprotonate to give me the kinetic one, 2 protons to give you the other one. So it's probability and accessibility. So that's where we've got these 2. We can use conditions, and we'll apply conditions where the left and right geometry are things we can select between. If you deprotonate under what we call thermodynamic conditions, where equilibration is possible, you'll always get the more substituted enol. If you deprotonate it under fast, irreversible conditions, you will get the kinetic one. Just generally, kinetic would be things like LDA, super strong, fast bases. Think this go back to Wittig and stuff like that. Irreversible, really powerful bases like LDA will typically favor your kinetic products. If I use something like hydroxide or methoxide, weaker alcohol bases, these will typically favor your thermodynamic products because these are cases where you're making this acid-base deprotonation at that lower center. Okay? Okay, we got one more problem for later. Oh, that's it for today. I thought I had one more. Oh, well, you guys are lucky. Okay. I'll see you guys on Wednesday. Okay, so we're going to go through the examples for today. So first off, in this case, we're starting off with our precursor molecule. We're treating it with a base, and then we're bringing in another component. That's how we're reading this component out. Now, if you should recognize this, this is the precursor you need for an HWE reaction. You're using weaker bases. Yes, we've got LDA as a possible one, but we've also got as options these other weaker ones too. So just trying to emphasize that you're going to need a base. Yes, you can go completely crazy. These guys will work just fine. You have a bunch of options. So the choice of the base is not the most important piece here. You just need one. So after that first step, we're just going to call addition of a base. We're going to get our double bond phosphorus, double bond R group, whatever that is. We will have our negative charge here. This is our HWE reagent. And remember, it is delocalized all the way through here. It is stabilized through that entire part. So this is our resonance stabilized nucleophile, and now we're going to bring in our electrophile. So the second addition, what we have here is an aldehyde where we have a hydrogen and an R group. And when we do that, we're going to lose our oxygen and our phosphorus as for the other fragment. So just to map out the pieces, my electrophilic carbon center, my nucleophilic carbon center, my oxygen part, and my phosphorus over here. So I'm going to have a new bond between my green and my red, or my fuchsia carbons. So we're going to have an olefin there between those two. And that fragments, the other stuff that's attaching to it, on the nucleophile side, we're going to have our carbon. It's going to have carbonyl R and hydrogen. And then on the electrophile side, you have a double bond out, and I'm going to draw this as two possible geometries. Let's say one of them is my, like this, where I have my methyl, and then the other possible one, again, I'm not saying this is the product, we're just trying to emphasize the formation of this double bond across here. The other geometry about this double bond that might be possible would be double bond hydrogen and carbonyl R H. So all I'm trying to emphasize is we have our oxygen trans to, or the carbonyl, excuse me, here trans to the methyl group, and we have the carbonyl cis to the methyl group. If you remember, based on the rules we expect, since this is a stabilized nucleophile, the preferred geometry will be the trans geometry, where the two large groups are opposite, the two small groups are opposite each other. That's the thermodynamically more stable one, making that the only product we expect in this case. Now for this one, we're asked to find which one of the reagents, either the Wittig reagent or the HWE reagent, was used to make the corresponding products. Now there's two things you want to watch out for picking these two things. One is the geometry, right? Like we've said, Wittig reagents will typically put large groups or bulky groups cis to each other, and HWE will typically put this sterically larger groups trans to each other. The other one to look for too is signatures of having resonance stabilization on one of the two sides. Remember, the HWE typically leaves behind a signature carbonyl, right? If this was my nucleophile, that group is lost in the elimination, which means this whole chunk right here gets transferred. So having these carbonyls left over can be a good sign that we were doing an addition from an HWE kind of reagent. So it's both the relative geometry, but also the constituents. Missing this carbonyl group here is a good sign that we probably did a Wittig reaction. So let's take them one by one. In the first case here, this should be pretty easy. Double bond, we have a bulky group and a bulky group. They're cis to each other. This is definitely our Wittig, right? That's A. Over here, we're missing any of that kind of carbonyl constituents. If you look at all the different fragments, we have just simple carbon-containing pieces. On top of it, yes, we've got a bulky methyl. These two are identical. So there's no cis or trans that we have to deal with in this case. This is best described as simply a Wittig reagent, just because there's no stabilizing groups adjacent to my double bond. In this case, we have kind of the opposite. We have this carbonyl fragment here attached to the center that could have been our HWE, so that starts to look like, you know, we had a HWE reagent where that was embedded into it. So it'd be fully appropriate to say that, okay, it's B because this side has a carbonyl that probably came from something like this, where maybe we had a reagent like that, where we have a methyl and this carbonyl attaching to the same side. So let me redraw that. It's like we've got a methyl. That would be the part that gets transferred to give us this whole fragment right here. Now, one thing that looks a little bit odd, this is a methyl group here versus this whole group here is a sp2 ester, right? That's definitely, or excuse me, in this case, this ester is on the same side as the much bulkier isopropyl. In this case, it's still likely, or you'd be correct to say that it was created from an HWE reagent, again, because we're coming in with this sort of carbonyl. In terms of the size, if you go back and look at the A strain, or the relative steric volume, a methyl group sitting closer to that center relative to this sp2 center. Remember, an sp2 center has a geometry where it's a flat plate. This methyl group is actually a tetrahedron, right? It's actually tetrahedral, which means it has lateral presentation. It's like a little umbrella compared to this is a kind of a flat plate. Because of that, steric volume of this methyl group, even if with these as hydrogens, is a little bit larger than the relative sp2. So in fact, in this presentation, that is my big group. This methyl is actually my slightly larger, at least equivalent, almost identical size between the two. So it's kind of a toss-up in this case. But again, if I had to look at this and say, how was this formed, you'd be correct to say it likely came from an HWE reagent, because HWE reagent is going to have a carbonyl stabilizing the nucleophile at that center. In this last example, everything is kind of following in the right direction. We have a carbonyl, and we're actually checking a hydrogen versus bulky group over here. This is probably a little larger, or again, similar size compared to the methyl group. So large group versus large group, they're on opposite sides. So we have two things that are sort of pointing to this being an HWE reagent. So that would be also B. So for this one, we're starting with a similar starting material, and we are doing two different possible reactions. In the first case, going this way, I'm replacing this aldehyde with this fragment, and going that way, replacing this aldehyde with this fragment. And if we're asked to fill in the reagents, if you look at the two, going first of all to left to right, that replacement, if you look at what we've formed, we've got two different groups. The two bulky groups are on the same side. The fragment we're bringing in here on this side, remember what we're really missing here is we've designated this as my electrophilic center. I need my nucleophile. So in this case, I'm going to be bringing in the carbon fragment with my aromatic ring, CH2 here, CH2 here, so that's carbon 1 and carbon 2, which makes that PH 3 plus and minus. That's the Wittig reagent that I'd be using to do this addition. Now, you'd also be correct by saying that, okay, well, I'm not just going to start from here. I would actually form that. So in my first step, I might take my iodide plus triphenylphosphine, and then second step, LDA. That's going to make this reagent, which then I'm going to couple together to form this compound. Now, important thing to do when you're discussing this too, notice that we are reacting under these conditions. If I formed this nucleophile, that nucleophile is going to select for this aldehyde. Look down here. What is that group? Remember, we talked about this in the first couple lectures. That is my acetal. That's actually a protected aldehyde. Most important is that center does not react. So the thing we're trying to emphasize here is we can not only choose the geometry of the product, that's based on Wittig versus HWE, the constituents of the product, that's what gets attached to my carbon center, that's how I bring that fragment in, and then the regiochemistry, where that reaction actually happens. By protecting this aldehyde as an acetal and leaving this one exposed, I would be able to react at that center and then carry it through. So this is just showing you how on a multi-step transformation it's possible to cap one aldehyde and then potentially carry this part through. In the other geometry, going to this one, or down here, that geometry gives me an addition. My nucleophile in this case, notice, has a electron stabilizing group attached to it. So that might come from something like the HWE reagent, where we have, let's say, O-ethyl on both cases. So here, this reagent plus, let's say, sodium hydride would give you my nucleophile. That nucleophile would then carry out the addition. Notice here that the two bulky groups are also trans to each other, and again, signature of the electron withdrawing or the resonance stabilizing group attaching. Now for this one, we are asked to find the enolates that could form under basic conditions. So by using a base, we're going to go through a mechanism where the protons, either these ones here or these ones here, can be deprotonated. Deprotonating from the green center, this would be like a kinetic deprotonation, would form an enolate like this, which is going to be resonance stabilized. You can also draw it as the carbanion to that center that's of deprotonation at that methyl center. From the other alpha center, we make an enolate like this. Again, let's draw it as a trans geometry where we've got resonance stabilization to make the carbanion represented this way. These are the two possible geometries for deprotonation to make my enolates. Same rules as apply for the enols. Under basic conditions, the enolate, it would generally be more stable, so we've added a stoichiometric atom base. It will sit as the anionic structure. And again, if this was under equilibrating conditions, the thermodynamic enolate, or this general enolate here, would be the one that persists. Under kinetic deprotonation, the kinetic enolate, the one that you can more easily access, is the one that we're going to typically form.